speaks to really, at the end of the day, how many letters of the alphabet plus punctuation plus uppercase and lowercase can ASCII, or really can computers, support? Well, it looks like 72% or so of you think that the answer is 256. And it is indeed the case that you can represent 256 possibilities. Why? You can actually do out the math. If you've got 8 bits, each of which can be a 0 or a 1, that means you have 2 possibilities for the first, times 2 possibilities for the second, times 2, times 2, times 2. That happens to be 2 to the 8th, or 256. It's fine if that's not immediately obvious, but if you do have 8 bits, each of which can be one of 2 values, you can come up with 256 possibilities. Those of you who chimed in to say that the answer is 255, in this case are wrong, only because now we're talking about the total number of patterns, which is indeed 256. But the highest value we could represent with 8 bits or 8 light bulbs, it would seem to be indeed 255. And that's because of all of the different patterns we can permute. But let me open the question to the audience now. Why might a US English keyboard be especially limiting? And in turn, why is ASCII really not quite appropriate when it comes to representing human language, even though this is what computers began with years ago? What is missing from ASCII? Why might 256 total possibilities not be sufficient? Kevin, can we go to you?
Sure. I mean, for one thing, I'm missing a lot of the accents that are in other languages. But if you just consider like Asian languages, there are a lot more than 256 characters.
Exactly. So not only are we missing accented characters that you might need in some languages, we're also missing the characters that you might need in Asian languages, in languages like Arabic and the like. There are way more symbols that we humans use to communicate in print and electronically than 256. English we can get away with fitting into this keyboard, but not once we introduce things like these characters, let alone other symbols as well. And it turns out there's other things we humans like to say these days and express using characters that have come into vogue, which is namely these things. Odds are probably sometime today you have sent or received one of these things here, otherwise known as an emoji. Now, even though these emojis look like pictures, they look like images, and they are technically, the way they're implemented in computers is actually as patterns of zeros and ones. These are actually just characters in an alphabet, the emoji alphabet, which is to say there's some pattern of zeros and ones that represents each one of these faces and the many other emojis that nowadays exist. And this is because the world has transitioned over the years from ASCII, which only used 7 and in some sense 8 bits total to represent all possible characters, to using either 8 or 16 or 24 or even 32 bits. Nowadays, there's a system called Unicode, which humans have come up with that support not only English, but also all of the human languages is the aspirational goal, both written and written in print or electronically is the goal. And in addition to that, this is to say we can represent things like this. So this is the so-called face with tears of joy. And this face of tears of joy, as of last year, was the most popular emoji sent via text messages, emails, social media, and the like. But at the end of the day, all you're receiving is like a key on a keyboard. So in fact, you wouldn't know it to look at it. But in fact, the decimal number representing this face with tears of joy happens to be 128,514. So to Kevin's point, to represent not only certain human languages, but certainly these emojis, we need way more than 256 characters. So we can use not just 8 bits, but 16 or 24 or 32. That's a huge amount of possibilities now. In fact, now, to really take the fun out of these things, if you receive that face with tears of joy or send it, you're technically just sending a pattern of bits that looks like this. That's all that's going on underneath the hood every time you use these things. All right, so we started again with electricity. We then represented numbers. Now we have the ability to represent letters and even emotions in the form of emojis. What else is there out there? Well, the emojis themselves, of course, at least the ones we've looked at, are pictorial in nature. And so that invites the question, well, how does a computer represent things like color? Like that face with tears of joy had a lot of yellow in it. So how is yellow, or any color for that matter, represented in a computer? Well, let me ask the audience again. If all you have at your disposal is bits, zeros and ones, and we just, as humans, need to agree how to represent colors, what might be one possibility? It doesn't need to be the answer, but what might your own instinct be if designing this for the first time yourself? How might a computer represent colors now? Yasmin, what do you think?
You would like assign numbers to different colors and shades and just use the same system?
Yeah, exactly. Perfect instincts. You would just assign numbers to the different colors, and we all just have to agree on what that mapping is actually going to be. So it turns out there's different ways to do this. And if any of you are artistic and use Photoshop or the like digitally, you're probably familiar with acronyms like RGB, red, green, blue. But there are other acronyms and other ways to implement Yasmin's idea where we just somehow map zeros and ones to actual colors. Well, RGB just happens to represent red, green, and blue. And this is a system humans came up with years ago that says, you know what? We can actually get every color of the rainbow by mixing together some amount of red and green and blue light, essentially. So that just invites the question, well, how do we represent the amount of red? How do we represent the amount of green? And how do we represent the amount of blue? And we have, as Yasmin says, bits at our disposal. So we just have to decide how to do this. So suppose we receive a pattern of bits that's 72, 73, 33 again. But this time it's not in an email. It's not in a text message. It's in the context of a file that I've opened in Photoshop. So it's as though I've opened a photograph that someone sent me. And I want to do some editing. And I see this pattern of numbers or in turn bits. Well, what is that representing in this case? In the context of an email or text message, it's still high. But in the context of Photoshop or Instagram or anything that is oriented around images, it's actually going to represent some amount of red, some amount of green, some amount of blue. And as we discovered earlier, the total number of possibilities you can represent with 8 bits happens to be 256. The highest value you can represent is 255 if we start counting from 0. So this is to say that each of these 3 numbers is a number between 0 and 255. So 72 feels like a medium amount of red. 73 is like a medium amount of green. 33 is like a little bit of blue. And if you combine those 3 amounts of color, 8 bits plus 8 bits plus 8 bits, using 24 bits total, using the first third to represent redness, the second third greenness, and the third third blueness, you get, it turns out, a dot that looks like this, a yellow dot. And so indeed, that emoji, when it's being displayed on the screen, is the result of the computer interpreting the 128,514 value as knowing, oh, that's the emoji with the face of tears of joy. But when it comes to displaying the information on your screen, now your computer is going to be using different patterns of bits to control the colors of the dots on the screen. And this term you might already know. The dots you and I see on our computer screens or even TVs these days are called pixels. They're tiny little squares that represent some color, such as this yellow one here. And you can actually see them in some contexts. If I go ahead and pull up this same face with tears of joy and zoom in a bit more, and really zoom in a bit more, now you can actually see what we call pixelation. And odds are you have seen this on Facebook, Instagram, wherever you might be resizing or editing photos that don't quite have enough resolution. The resolution of an image is just how many pixels or dots there are horizontally and vertically. So if you really zoom in on an image, you'll eventually see those pixels. And this is to say that even in this zoomed in happy face, there's a huge number of yellow dots and a whole bunch of black and gray and brownish dots as well that compose this very colorful image. And so you can see them in that case. And every one of those dots now, a pixel, is using, I claim, like 24 bits or 3 bytes. Now, you can imagine there's probably, hundreds, maybe thousands of dots in that image if we zoom out and look at all of them again. So if every one of those dots or pixels is 3 bytes, this is why the photographs you and I take and the images you and I download from the internet are typically measured not even in bytes per se, but in kilobytes for thousands of bytes, or megabytes for millions of bytes, or if it's a video file, it might get even bigger, billions or gigabytes. But that's all that is happening underneath the hood. We're just representing information in this way. Well, let me ask a follow-up question now. If we've now, thanks to Yasmin, represented colors and in turn images, because all an image is a grid of pixels. You take the same principle Yasmin proposed, where you represent each color of a dot, and you have a whole bunch of dots. That gives us images. How would you propose computers represent video files? Again, even if you don't know the answer, how might a computer represent video files now using, again, only bits at their disposal? Who might like to field this one? How might a computer represent a video? Justin, what do you think?
Maybe just like rapidly changing the bytes.
Just rapidly changing the bytes? And I hear, can you elaborate a little bit? What do you mean by changing the bytes?
like rapidly changing the RGB of individual pixels.
Exactly.
To match the image of that second of the video or portion of the video.
Perfect. So if you think about like the rectangular screen that is your phone or your laptop or your desktop monitor, if you just keep changing the colors of those dots once per second or a whole bunch of times per second, we'll get the illusion that there's actually motion on the screen, ergo video. So really a video, in some sense, is just a whole bunch of images, to Yasmin's definition, flying across the screen really quickly. And so you can see this even old school style. For instance, let me go ahead and open up on my screen a short video that represents a flip book. So you might have made one of these as a kid, or maybe your teacher did, or you saw them at least in person somewhere, where if you take a whole bunch of pieces of paper and staple or clip them together in some way, draw a whole lot of pictures, all of which are similar but slightly different on each page, you can create an animation or really a video. And this is all a video is in the purely electronic world. Even though this happens to be implemented in paper, what happens in the computer world is indeed just a whole sequence of images flying across the screen at some rate. And that's what actually gives us the video files that you and I know today. And there's even more rabbit holes we can go down. For instance, how might you represent music? Well, music could be represented, gosh, in different ways. Like if you've played the piano, for instance, you might know that there are notes like A through G, but there's also sharps and flats and so forth. But you know what? Maybe we just need a number to represent each of those possible notes. And maybe also we could use another number. Just like images use multiple numbers to represent dots, we could use a number to represent the note in a song, but also another number to represent the duration of that note. How many seconds or milliseconds or beats should you hear that note for? So you could come up with other formulations too, but music really can be quantized in the world of computers into just small pieces of information. And so long as you and I agree on how to represent it, that's how these things all work. And if you've ever wondered why there are JPEGs and PNGs and GIFs and Word documents and Excel files and all of these different file formats or file extensions on computers, those file extensions or formats just represent a whole bunch of humans agreeing how to store patterns of zeros and ones in a file so that when those zeros and ones are loaded into a computer for display or for interpretation, it knows what those patterns represent. Images are represented slightly differently. Sound and video are represented slightly differently. But it's all zeros and ones